Okay, so let's start out by talking about the kinematics of a particle, and I'll get to what the word kinematics means in a moment. But what we're doing here in dynamics is taking another step up the mechanics ladder. So, as you know, you must have come from statics, and that's where all of our forces equal zero, meaning everything was in equilibrium. That also meant that the sum of any moments that you had was also zero, meaning it was not rotating, also in equilibrium. That's not the case here in dynamics. In fact, when we sum our forces, we're going to get some change in momentum with respect to time. And this can be interpreted or derived a couple different ways, but we're going to first look at if momentum is mass times velocity, then we can pull the mass out and say this is the derivative of velocity with respect to time, giving us Newton's second law for the summation of the forces is equal to mass times acceleration. And we'll see that we have a similar summation of the moments will give us some I alpha. And we'll get to this one later. Right now we're just talking about point masses. We will later move on to rigid bodies. Okay, so what does that mean? That means that we have an imbalance of forces or an imbalance of moments causing an acceleration. We can break this up into three components, or depending on our coordinate system, change the coordinates around. This also means we're going to have an angular acceleration if we have an imbalance in the moments applied to a body. So the primary focus of the first two chapters of this class are just going to be dealing with Newton's laws, primarily Newton's second law. Okay, so a lot of this has been covered in your previous physics classes. Hopefully this is a review, but bottom line is I have to reteach this every semester. Otherwise my students will not succeed in general. So even if this is a review to you, I recommend taking a look at it still, because I'm going to probably dive a little bit deeper. But the goal of this is to find some methodological approach. I couldn't say that. Methodological approach to solving any problem. And any problem, you'll find out as an engineer, you become problem solvers in general, or a physicist, you're a problem solver in general. And the same approach that you can apply to a physics or engineering problem can be used to solve any life problem. So that's a goal we want to get out of this class. We're going to present this in two parts. The first is kinematics. I'm not going to quiz you on which one is which, because they're very similar. The next is kinetics. I am not good at remembering one or the other type things. Kinetics and kinematics. We're going to start with kinematics because it studies only the geometric aspects of particle motion. So only the geometry of particle motion. And this is going to be chapter 12 stuff. Then we're going to move into kinetics, excuse me, in chapter 13, and this is going to involve the analysis of forces. And these forces cause accelerations. Okay, so we're going to learn how to work with the equations in chapter 12. We're not going to worry about how the accelerations come from or what they come from. In 13, we're going to have to draw free body diagrams like you did in statics, some forces, and then that'll give us the equations to find the acceleration. And then we can use kinematics to find out more information about the motion of the particle. It's actually very important to look at the history of this stuff. Back in like 384 BC, we had Aristotle, and he was not a physical scientist of any significance. He believed in air, wind, fire, and earth powers, and if you lifted a rock off the ground, it fell back to the ground because it was a rock and it wanted to be back with the rest of the rocks. And most of his philosophy or laws revolved around that. The first major contributor to dynamics would be Mr. Galileo Galilei. Yeah, that's it. And that came about, he lived 1564 to 1692. And he's known as the first scientist, the first physicist. He observed moving bodies in the sky. He worked with pendulums, falling bodies on the earth. He really had the first grasp on physics. But then Sir Isaac Newton came around. With others, he didn't do this alone, but he formulated the basic gravitational laws and laid the foundation for the fields of dynamics and calculus. Euler, and D'Alembert, and Lagrange were also classical mechanics contributors, and as you go through different classes in dynamics, you'll study something called the Lagrangian. I spelled that right. Lagrangian. And it's a way of using only energy methods to solve these type of problems. But this guy this one right here is the one that we're going to focus on the most. I'm going to go ahead and spit these out, even though we're not going to really use them until chapter 13. This is how I was taught them in physics. Newton's laws, and I will test you and quiz you on these, I promise. If we sum the forces and they end up equaling 0, then the velocity should be constant. Most of you have probably heard the longer version, a little bit more difficult, and most people end up forgetting to write half of it. If an object is in rest, it stays at rest unless acted upon by an external force. An object in motion is in motion, or remains in motion, unless acted upon by external force. This is a way easier way of writing the same thing. Our second law would be that if we have a summation of forces acting on a body, it's going to cause that mass to accelerate. In statics, you had this term go to 0. Not in this class. We're going to have some acceleration. And one of the most useful, actually, we just don't realize we use it as much, is Newton's third, saying that every force has an equal but opposite reaction force. So the force onto 1 is equal but opposite to the force of 2 onto 1. The force of 1 onto 2 is equal but opposite to the force of 2 onto 1. And notice the vector signs. We're going to be working mainly in vectors. We can reduce some things down to scalars, but it's always best to work in vectors because that's where your future is heading. So where do we use dynamics? Well, structural design, vehicles, engines, machinery, anything that moves. This, I think it's a fascinating topic, and it's honestly what got me very interested into physics and into my academic career. Alright, I'm going to lay out some problem solving steps. The first is going to be draw free body diagrams. Okay, just like statics. This includes a coordinate system and some geometry usually. Go ahead and put step 2, establish a coordinate system. Should have the same as your free body diagram. Our step 3 would be apply relevant principles of physics. And then 4, to solve for the unknown. This could require calculus, and most definitely algebra and some more geometry possibly. Alright, that pretty much wraps up 12.1. Go ahead and read through it. There's always benefit to hearing or reading another person's words versus just the teacher's. Thank you.